All right, in this worked example, I'll be going through question 6 from paper 22 that was offered in October, November 2019. Part A reads, state Kirchhoff's first laws. This is where you just need to kind of have the good textbook definition in mind for which of Kirchhoff's laws is the first one there. And we say, mathematically, you can kind of think about it like this. The sum of the currents going into a point is equal to the sum of the currents going out of that point. And you want to kind of put that mathematical statement into, a complete sentence. The sum of the currents entering a point or a node or a junction. These are the three sort of interchangeable nouns you can use for that. The sum of the currents entering a point or a node or a junction is equal to the sum of the currents leaving that point or node or junction. Okay, the sum of the currents going in equals the sum of the currents going out. Charge is conserved. So Kirchhoff's first law is a consequence of the fact that like matter energy and like momentum, charge is one of those quantities which is conserved in our universe, not created nor destroyed. Question goes on to give us some data here. It says the variations with potential difference V of the current I for a resistor X and for a semiconductor diode are shown in figure 6.1. And so here we have this IV characteristic, right, where they're plotting I on the vertical axis. We can see that a resistor just has a straight line gradient, where a diode is another non-ohmic component. So we saw a filament lamp as an example of a non-ohmic component. Only things that have a straight line on these kind of graphs are ohmic. They obey Ohm's law. In other words, the current and the voltage are directly proportional, right? For a given voltage, there's a current and they go up sort of in proportion. That's not true with the diode, right? There's this sort of curvilinear plot. So Ohm's law doesn't hold for the diode. A diode is a non-ohmic component. The question goes on to read, determine the resistance of the diode for a potential difference V of 0.6 volts. So we always want to kind of answer the question the way it's asked of us, obviously. And so determine the resistance of the diode, and so that's this curve here, for a potential difference V of 0.6 volts. So if we locate that value 0.6 volts and we go up here, it looks like that neatly intersects right at that point. Okay. All right, which corresponds to a value of 7.5 milliamps. And we're determining the resistance of something. We can use Ohm's law, R equals V over I, to give us the voltage, 0.6 volts. And we read the current off at 0.6 volts as 7.5 milliamps. So we can write that 7.5 milliamps. A volt per amp is an ohm. A lot of the notes that I had to write to students that submitted their work last week were, convert milliamps to amps. If you're reporting ohms of resistance, that's a volt per amp, not a volt per milliamp. 0.6 divided by 0.0075 equals 80. So the resistance of that diode for a voltage of 0.6 is 80. And this is sort of the point for a diode, that the resistance changes at different voltages. Here, the resistance is constant, right? Like there's a constant slope of this. The inverse of the slope of this would be its resistance. Right? If I calculated the slope and took its inverse, that would be the constant resistance of this resistance. For a diode, the resistance changes, okay, depending on what voltage is across it. The question goes on to state, describe qualitatively the variation of the resistance of the diode as V increases from 0.6 to 0.75. All right, and so as the voltage increases from 0.6 here to 0.75 up here, what's happening to the resistance of this diode? Well, if we keep in mind what I just mentioned a moment ago, that if we did have voltage against current like this, that ratio is the resistance, right? V to I. We're given I of V though, right? So we sort of have this. So I over V is equal to 1 over the resistance. All right, this is an I, this is a number 1. So if we look at sort of the slope right here, the slope, all right, so it's like the resistance point. So we're saying raising it from, what were we asked to consider? Does anybody remember the question? From 0.6 to 0.75 volts. So at 0.6 volts, we have sort of this value here. And at 0.75 volts, to be kind of here. And we can see that this curve is sort of going up, but then it almost levels out there. And so we could maybe, make the assumption that, well, it tends to level out here, that if we were to take the slope, say at 0.6 or at 0.75, we might get sort of the same value, and 1 over that value will sort of be the same, because it is kind of going towards this straight line gradient there. But if we just sort of think about it like this, here the slope is clearly shallower, and then it's getting steeper and then steeper. Like this is going from a shallower slope to a steeper one. So if we took the inverse of this would mean really high resistance. Like if we had a flat line here, then that would be a slope of 0 or an infinitely resistant sort of resistor. So a line that's closer to flat on an IV characteristic indicates high resistance. A vertical line would indicate no resistance. And so this thing is actually decreasing, right? It's going from higher resistance to lower resistance as we increase the voltage. Okay, so as the voltage goes up, we're actually decreasing the resistance. It becomes less and less resistant to charge. That's how current is able to flow through a diode. Once we get to what's called a threshold voltage, in this case 0.6 volts thereabouts, it starts to conduct. Before that, it does not conduct. No lets charge go through one sort of direction. That's why they use this symbol for a diode. Let's sort of scroll down to it. So here they're showing you a circuit diagram. This is the symbol right here for a diode. And note that it looks like an arrow, kind of like an arrow pointing in that direction. That's because a diode really is used as kind of like a gatekeeper. They'll only let charge go through it one way. Because the current sort of going through it the other way, or the resistance going through it the other way, would be infinity. And so we'll basically resist the flow of charge in a direction. We use a diode as sort of as a gatekeeper to only allow the charge to flow through one way. So here we see a circuit, and it's telling us that the two components that we were looking at in that graph are here and here. So the resistor X that was graphed, the straight line, and the diode is this symbol. So that's the diode right there. They are in series on this branch, and then they're in parallel with another resistor Y. Sort of says that down here. The cell has electromotive force E, negligible internal resistance. Resistor Y is connected in parallel with resistor X and the diode. They tell us the current in the cell, 9.3 milliamps, and the current in the diode is 7.5 milliamps. Use the figure, it says actually use figure 6.1 to determine E. So if we know that there's 7.5 milliamps going through this branch, then there's 7.5 milliamps going through both the diode and the resistor X, right? So we locate 7.5, and we can see right here that there is 0.3 volts for resistor X. And we already saw that there's 0.6 volts for the diode at that current, right? That's the current that we sort of use to calculate the resistance for our diode. And so we can use this figure here. With the given current, right? They tell us it's 7.5 milliamps, and we're trying to calculate the EMF in the battery. So we know that the EMF is going to be the same as the voltage across every parallel branch. And so right here, you can see that that's the voltage of resistor X, 0.3 volts drop across resistor X. And if we go over here, we already saw that the 0.6 volts is what's dropping across the diode. So we have 0.6 volts dropping across the diode, 0.3 volts dropping across the resistor, for a total voltage drop of 0.9 volts. And Kirchhoff's second law tells us that the sum of the EMFs equals the sum of the potential differences. And so we've really just sort of calculated off of that figure is the potential difference across the diode and across resistor X, those two guys right there, that the arrows conveniently are pointing to, and they sum to 0.9. So we can deduce the EMF must be equal to the sum of those potential differences, 0.9. So 0.9 volts is the correct answer here. And again, we calculate that by realizing the sum of the EMFs is equal to the sum of the potential differences. These are the potential differences for these components when the current is 7.5 milliamps, right? And we read that sort of off of the figure like it asks us to do. The next question asks us to determine the resistance of resistor Y. All right, so determine the resistance of resistor Y. So resistor Y is this guy down here. The first thing that you should do is consider Kirchhoff's first law. The sum of the currents in equals the sum of the currents out. And we can clearly see 9.3 milliamps going into this node, this point, but only 7.5 coming out this way to go through this branch, which means all the rest of the amps must have went down that way. So what is 9.3 minus 7.5? 1.8 milliamps of charge would go through resistor Y. The same 0.9 volts that we just calculated up here for the EMF are also dropping across this resistor, right? Because we know that the voltage is the same across parallel branches. So we can determine the resistor of Y as the voltage divided by the current. The voltage is still 0.9 volts. The current going through resistor Y is 1.8 milliamps, or 0.9 volts divided by 0.0018 amps. This was the conversion that you all needed to do to get your lab work correct last week. You needed to convert those milliamps into amps to get ohms of resistance. So 0.9 volts divided by 0.0018 milliamps is exactly 500 ohms. The resistor Y down there has 500 ohms of resistance, and again, that is calculated as the 0.9 volts divided by the 0.0018 amps of current. Okay, and again, you get this 0.0018 by taking the 9.3 minus the 7.5. All right, 1.8 milliamps. Question goes on to ask us to calculate the power dissipated in the diode. Power dissipated in the diode. Okay, do that. Well, we kind of know both I and V, so we'll just use that one. So the current that went through the diode was the 7.5 milliamps, or the 0.0075 amps of current, times the voltage across that one was 0.6 volts. 0.0075 times 0.6 gives us 0.0045 watts. So 4.5 by 10 to the negative 3 watts. So remember, there are three equations for power we talked about. I times V is one of them, I squared R, and then V squared over R. And any one of them would really work for this. This is just sort of the easiest one because nothing's squared, so that's pretty easy. All right, and then this last one is the one that really kind of stumped me for a bit. It says, the cell is now replaced by a new cell of EMF 0.5 volts and negligible internal resistance. Use figure 6.1 to determine the new current in the diode. So keep that in mind, that it's like we take this circuit right here and we take out our 0.9 volt power source and we replace it with a 0.5 volt. Like we decrease the voltage EMF. We still got the same circuit. Okay, and now it's asking, well, instead of 7.5 milliamps, what are going to be the milliamps through this branch here? And that's really the key. The first thing that I did, which was incorrect, was just kind of very naive, and I said, okay, well, if they change it to 0.5, just read it off the graph. 0.5 is this. And I thought, wait a minute. These are both in series with each other along that branch. In other words, I can't just use the new voltage and read off the graph what the current is. I have to consider the fact that that voltage has to drop across both those components, right? Like there's both a diode and a resistor on that branch. So I can't just go to 0.5 and read it off. It's not as simple as that. Rather, here's what you need to do. And this is a really tricky one, and I would pay close attention to this in case you had a similar question, on the quiz. If we know we need to add up to 0.5 volts, but it has to be the same current going through both ones, that's the key. Like I could say, well, I could add 0.3 to 0.2, but then I have a current of like this much for the diode, and the 0.2 would be this much. That's not the same current. I have to be able to draw a line through like the same current, so a horizontal line, such that the voltages add up to 0.5. And if there's a better way to approach that besides that strategy, and you figure it out, let me know. Because I don't know of another way. Like we have to add up to this 0.5, and if you just kind of look here and you go, okay, well, 2.5 milliamps, look, we get a 0.1, and we get a 0.4. So see, if you draw a horizontal line, just like there has to be a horizontal line somewhere along this graph that's going to give us the same current through both of them that adds up to that. And so that's what we're really looking for, that with the answer here is 2.5 milliamps because the voltage drop across my resistor is 0.1 volt at that current, and the voltage drop across my diode is 0.4 volts at that current. And so 0.1 plus 0.4 equals the total voltage drops that I need. And it's the only set of values that keeps the same consistent current, which is a requirement for a series circuit. And so I sat there and tried to calculate it, 5 different times before I said, well, there's something else to this that I'm missing here. And indeed, I think that's the path to the solution. This sort of upon inspection of the graph, you have to see sort of the horizontal line that, there's only one sort of solution that sort of works there. And I bet you there is a more elegant path to the solution. So leave it down in the comments below.